Good morning, students. This is Venkatesh Kesi, Assistant Professor, Department of Mechanical Engineering, BITM Bellary. Welcome to the class of Experimental Stress Analysis. The subject, Experimental Stress Analysis, is an elective for 8th semester students. As the name indicates, the stress analysis of body by using experimental techniques. Now, in the modern world, we are able to create complex man-made structures like multi-store buildings, huge ships, and the new models in automobile sectors. Even we are able to create or we are able to send a advanced what you call as planes, advanced planes, as well as the new rockets into the space. This is our confidence in the modern engineering field, where the man-made structures had taken for granted. See, this is what the attitude have made the engineers to the tribute to the competence and reliability of the modern engineering. This is what the ability of the modern engineering. Now, for this analytical or the analysis of stresses, either the necessity things is your mathematical analysis of stresses for regular bodies or regular shapes, right? But in complex components, it may not be so. In practical, what all the considerations which we have done for regular geometry cannot be applied. But if there is no way, any other way for an engineer to study the stress analysis, or to study the stresses, you need to have the resources or previously existing resource. But the new materials or the new designs in the practical world cannot be applied by our old techniques or old methods of stress analysis. In these conditions, to make a member under what you call as under safer working conditions, an engineer is able to build a great strength materials great strength materials, which is necessary, of course, which is necessary, but to prevent its failure, what does the engineer do? He'll be considering the factor of safety, the high factor of safety, which finally leads to, when we are considering the high factor of safety, which will finally leads to a high weight in the machines, what you call as components, and the large size of the components. These both weight and size of the component, which will lead to the high investment or the material cost, which will be affecting the total overall cost of the component or either a machine or other component. So it is very necessary to analyze the stresses in the components, and which it is able to determine the stresses in the component with the minimum cost, then it is a feasible way. So in these conditions, we need to analyze the stresses in a component. The stresses in the component indicates here the 6 stress components stress analysis involves, because we know what is stress. Stress is nothing but the internal resisting force for an externally applied loads. So when we consider a simple geometry like a bar, a cross section, a circular bar which is being applied by an external force, tensile force F, then everyone can say that stress is directly proportional to strain, or stress, what you call as stress, is nothing but the force by area. Now if I am able to mount it in horizontal directions, I can determine sigma x, that is a stress along x direction. If I am able to mount it in vertical direction, I am able to determine stress along y directions. But for a component like a 3-dimensional body, I need to determine the stress at different points. The stress at different points. Then I'll be considering the stress tensor. Here the stress tensor is nothing but which is involving the normal stresses as well as the shear stresses. See here the stress tensor which involves total put together 9 stress components. But when we are considering the symmetry of the stresses, the total 9 stress components will be reduced to 6 stress components. 6 stress components. That is what, because of the symmetry, we only have 6 components. These all things we have learned from our regular, what you call as basic subject called as strength of material. Similarly, we can determine the 6 strain components in a body, strain components in a body. So for this one, if I need to determine the stresses at different points and different orientation, we need a lot of informations, right? Because if it is a regular body, this is a regular body, and I need to analyze the stress. Even though if I am applying an axial load, I need to determine the lateral strains in 2 mutually perpendicular directions. Then such a solution is known as closed form solution. Closed form solution. Suppose if I am considering a problem like a plate which is having a circular cross section at certain point, which is having a hole of radius r. Such problems, in these conditions, I cannot apply stress is equal to force by area, because the material may not have the uniformly distributed area, and we cannot indicate the stress where it is dependent directly proportional to the applied load, because of its a circular hole which is being created at the center of the plate. So in these conditions, it has been very difficult to get an exact solutions. So here there are possibility of stress analysis, and this possibility of stress analysis can be done in 3 different methods. One is analytical method, numerical method, and experimental methods. See, in analytical methods, Analytical methods which we are taken from our regular what you call as mechanics of machines or strength of materials, or even from a theory of elasticity, where we are able to get a conceptual appreciation of the stress fields. But here, these analytical methods are restricted to solve only for a limited problems or a limited what you call as regular geometry problems. But this cannot be applied for a complex geometric problems. So along with this one, suppose if I am considering a bar with the axial loading and if I am applying a torque, that is a combined loading. Or for example, if I am considering a plate with multiple holes, our regular analytical techniques cannot be applied. Similarly, a different what you call as a beam which is being applied by a point load, because all the analytical methods which we are considering is dependent upon certain assumptions that which we have learned from our basic MOM, mechanics of machines, or SOM. See, such assumptions are either it may be plane sections remain plane before and after loading, and the second one is beam material or any material, beam material is perfectly homogeneous and isotropic. And the third one, it may be material is stressed within elastic limit and which obeys the Hooke's law. So here, what all the analysis which you are discussing here, this is restricted for analytical methods, where which will be dependent upon certain assumptions, and which are limited. This analytical methods is limited for simple geometry and simple loading. And the second method, which is a numerical methods which provides a scope for solving problems with arbitrary geometry or a complex geometry. And what are the output results we are getting? It will be in terms of an approximation values. See, this you have learned in your previous semester, that is finite element methods or finite element analysis. So here the numerical method can be classified into three broad classifications: finite difference method, finite element method, and boundary element method. But these methods are validated by comparing the results from the output with the experimental techniques. This one alone, numerical methods cannot satisfy the requirements. So once it is validated with the experimental techniques or experimental methods, the numerical model will be an ideal form for solving any parametric analysis. This is what the advantage of a numerical method compared to the analytical method. So this one, once if I am once we have validated it, several geometric parameters can be varied, such as loads can be changed. And one problem with this one is the numerical approach must be handled very carefully, because it may give up the errors in the output values, and these errors which are being in the output because of the improper considerations or constraints in the body and improper locating of the nodes or the key points. So only numerical technique alone cannot satisfy the requirements. So to overcome this one, we have the new technique called as experimental technique. That is what our subject is, experimental stress analysis. See, these techniques of stress measurement and analysis, which consist either as a reassurance testing of completed structures, and here the prototype of any body can be analyzed very easily, and whether we can build based upon the existing analytical knowledge and the past experience. So the large components can be scaled down and we can predict the stresses in the members. So now let us consider one small example where the nut is tightened by a spanner. Here the stress is because of the tightening. One end if I am tightening and other end we are applying at free end, we are applying the load. Because of the application of load, there is a stresses developed in both the nut as well as the spanner. So for your analysis in a clear picture how the stress is distributed, we shall consider the material of both the spanner as well as the nut as a epoxy material. Epoxy material where we can clearly understand how the stress is distributed. The stresses are can be analyzed, or we can observe the stress in the form of finely bifringent, what you call as a design or a pattern. You can observe here, depending upon the loading, how the stresses will be distributed in the nut as well as the spanner. You can observe the first one, when the load is being increased from 1, 2, 3, 4, fifth loading, that is a 5 Newton or 5 kg whenever we are applying the load, and gradually when we are increasing the load, you can see the stress patterns are varying at different points. You can observe the stress concentration are maximum here at this point, or at this point you can observe. And similarly, the outer surfaces, you can see the stresses how they have been distributed. So this is what the experimental technique where we can practically analyze the method without implementing any of the formulations or any of the formulae or any of the numerical equations. Directly we can predict the member where the stresses are locating maximally, and we can concentrate on these areas by considering the experimental techniques. So when we are viewing the combined loading of the spanner as well as the nut, here the basic fundamental is from your physics, that is the optics, and we can observe the fringes developed in the members or the components, and these fringes are clearly observed. You can observe, when you observe clearly, you can observe the fringes. These fringes will indicate what is the amount of stresses induced in the member. See here, the results can be obtained very clearly by observing the contours, and when we are tabulating these values without any differential equations. This is what the advantage of experimental stress analysis. In the next class, we will be discussing in detail about what is experimental stress analysis. Thank you.